Hello, everybody. Welcome to the Topological Complexity Seminar, part of the Applied Algebraic Topology Research Network. Our speaker today is Nursultan Kuanyshov from the University of Florida, who will speak on the sequential topological complexity of group homomorphisms. Take it away.
Thank you for the warm introductions, and thank you, Professor Gonzalez, for invitation. And it's my honor to give a talk in one of these prestigious seminars. And as Professor Oprah said, my title is on the sequential topological complexity of group homomorphisms. And my talk is mostly going to be on this paper on the sequential topological complexity of group homomorphism published in Topology and its application. And I'm mostly going to speak about these four invariants, and each invariant at Lusternik-Schneemann category, cohomological dimension, topological complexity, introduced by Michael Farber, sequential topological complexity, introduced by the Rudiak, and each of them are interesting by their own. In here, I would like to relate each other. Okay, so I split it into three parts. So the first part is the topological complexity of map, introduced by Jamie Scott. And the second part, we're going to talk about LS category and the cohomological dimension of group homomorphisms. And the third part is the sequential topological complexity of group homomorphism, where I present some computation for like a group homomorphisms of, namely for finite groups, finitely generated abelian groups, free groups, surface groups, nilpotent groups, and so on. Okay. The first one is like a topological complexity of introduced by Jamie Scott. So why did I choose that? As the experts are in here, like they already know there are like topological complexity of map is well studied, and for example, Peter Pavyshev has his own, and Jamie had his also like there's a different one. So I think here, like I would like to study his definition because his definition is easy to work. Namely, I stated here, like you can generalize almost all classical numerians from the spaces to the maps. In my cases, from groups to the group homomorphisms. For example, like in the paper, like I basically give a definition for like a notion that has been introduced, like a topological complexity of space, introduced by Michael Farber and John Opera. You can easily modify the definition to get at like a D topological complexity of group homomorphisms. Similarly, recently there is like a new invariant. It's called distributional or intertwining invariants, introduced by Tranishnikov and his student Ekanch. And so you can easily give they extend their definition to the group homomorphisms. And similar notions are introduced by Ben Knudsen and Weinberger. You can define their notion as well as for the group homomorphisms. And these are the important because the invariants they give the low bounds for the classical numerians for the spaces. So once we establish the theory for the group homomorphisms, the next step would be obviously to study this invariants. So lastly, I also put like amenable category. So you can extend it for the amenable category of group homomorphisms. Very easily. So and that's why I choose Jamie Scott. This is my motivation. So whenever we define this LS category, we would like to start with a sectional category, or it's known as a Schwartz genus. So let P be a fibration here, a Hurewicz fibration. The sectional category of P, denoted as C-cat of P, is the smallest integer K, such that B can be covered by K plus 1 open sets, and each open set admits these partial sections. Okay. And here we are using a reduce. Instead of asking like K open set, we are asking K plus 1 open set. So And from here, one can see that from algebraic topology, we know that any map can be turned to the fibration. So, for example, if I have a base point and that is included in the space, then I can turn this inclusion into the base point fibration. If I take a sectional category, I get like a LS category. Similarly, for topological complexity, you have a diagonal map, you turn it to the fibration, and you get topological complexity of space. And this is it's easy to state, but it's not a computational friendly. So I would like to use I think this definition. Michael Farber's a first paper in the topological complexity, and where he defines given a space, and we have a path space, or we call it a free path space, is a map from the interval to the space, and we consider free path fibration. What it does, it takes a path and evaluates at the initial point and the ending point. And definition is topological complexity of X denoted that TC of X is a minimum number case such that X cross X is covered by K plus 1 open sets, and each open set exists a continuous motion planning. So we know that a continuous motion planning exists on the space if only if the space is a contractible. In some sense, here, we are partitioning X cross X with a contractible sets. Okay, then Rudiak, they extended this topological complexity to sequential topological complexity, and he defined that his original definition is the following. So let X superscript GR be a path space where GR is a wedge of R closed intervals and where zeros are identified. Then he defined the sequential topological complexity of space to be just sectional category of this base point fibration. So where it takes a path, it evaluates at each intervals. Okay, and it's not hard to see this. His definition is the same thing as the following definition. Sequential topological complexity of X denoted TCR of X is a minimal number K such that X to the R is covered by K plus 1 open set. Each set exists a continuous motion planning. And here the fibrations are defined. You take a path and you evaluate it at each vertices. Okay, and it's known for the as exponential correspondence between these two path spaces. So for example, you have a path, what I call this is a component path. So here, you take a path, you can get a component-wise path. If you have component-wise path, you can get a path. So here, let me just state what I said it. So if I have a path from a path space, I can get a component path by using this formula. Okay, on the other hand, given a component wise path, I can concatenate it in the following way to get a path in this P of X. So where alpha i's are the inverse path. Okay. So the basic inequality in this sequential topological complexity is the following. And here I give four names. It's not a one paper, so it's Rudiak had the different ones. So Grigori, Lifton, Scherer, and Schwartz. So it's basically one says let X and Y be a path connected normal space. Then this a sequential topological complexity of X is bounded by LS categories. So above by LS category of X to the R, below by LS category of R minus 1. And we have a product formula, product estimate. So this is due to the Schwartz. And if the space is a CW complex for simplicity, because I will be dealing with only CW complexes. So we have the couplings. It's known as a zero divisor, and here it's a low bound for the sequential topological complexity. And number 4, it just gives the Garnier characterization. So sequential topological complexity is like less than n if only if this PR has a section. So like PR of n is defined like a fiber-wise joint. I'm not going over. So number 5 is interesting. Like a sequential topological complexity attains its minimum whenever X is a topological group. So here, like it's true that whenever X is a H space, this is a result of the Grigori Lifton and the Scherer. And here, in my cases, it suffices to just consider where X is a topological group. And in my cases, I would like to have similar result for my notion. So like sequential topological complexity of map. Or in order to do that, let me give a definition. So Jamie Scott gives the definition. So let F be a map from X to Y, and we call F motion planner on the subset U is a map from the subset U to the path space such that if I evaluate it at the like initial 0, I get first coordinate. If I evaluate it at the like 1, I get the second coordinate. The topological complexity of map denoted as TC of F is a minimal number K such that X cross X is covered by K plus 1 open sets. And each open set are F motion planners. If no such K exists, we say TC of F is infinite. So here's like I use it to pullback. So you can define it this topological complexity as pullback vibrations. And we want to talk about this. So one can state Jamie Scott's definition and come up with the following definition. So like let F be a map. We call sequential F motion planner on subset U is the map from the subset U to the path space of Y such that like if we evaluate it under each vertices, we get corresponding coordinates. And that, so from there, we call it sequential F motion planner. Then sequential topological complexity of map F denote that TCR of F is a minimal number K such that X of XR is covered by K plus 1 open set, and in each open set there are sequential F motion planners. If no such K exists, we can set sequential topological complexity of map to be infinite. Okay. From this, like until like this definition is like I have a characterization for this definition. So let F be a map from X to Y, and let U be a subset of X to the R. The following are equivalent. The first one is that there's a partial section, and where U goes through to the pullback of vibration. In other words, number 1, it just tells you that you can define this into like a pullback vibration. So remember, like this path spaces are like a construction is a factorial. So now you can have a py you pull it back along this way. So now we can define sequential topological complexity of map to be just a sequential category of this pullback vibration. Okay, and number 3, it tells you that like if I have an image of this, and if I take projections maps are homotopic. And number 4, if I have this map, if I restrict it on this subset U, I can deform this into a diagonal of Y. And the number 5 is like there is a map H from U to the X such that if I take a composition of this F to the R diagonal of H, this is homotopic to this F to R restriction to the U. So basically I obtained it like Jamie's like I think generalized analog. And that like in Jamie's case, he didn't have number 3 because he was only working on topological complexity. And this number 4 is like I think number 5 is like Murita-Wu notions for topological complexity of map, and I can have similar ones on here as well. Using this characterization, I was able to obtain the following results. So like if I have a map, then this the sequential topological complexity of map is the minimum of the sequential topological complexity of spaces. As we can see, it behaves how it behaves LS category of map, namely or similar topological complexity of map. And similarly, I can obtain like an analog of Rudiak result. So in other words, sequential topological complexity of map is bounded by LS category of this maps. So above by category of F to R, below by category of F to R minus 1. Similarly, I have this cap length formula to estimate from below. And for if I have a composition of two maps, I can have this is less than or equal to minimum of this sequential category or a sequential topological complexity of maps. Okay, and similarly, sequential topological complexity of map attains its minimum whenever F is a group homomorphism of topological space, topological groups. Okay, and this is a part one. So I think the theorem is expected. Probably the expert knows this one already. So and let me move to part two. So this is like a LS category and cohomological dimension of group homomorphisms. So let me define LS category of map, denoted that cut of F is a minimal number K such that X admits open cover by K plus one open sets. And if I restrict it on each open set, the map is null homotopic. So as we can see, if I take the identity map, I recover LS category of space. And once I have a definition for LS category of map, I can easily define LS category of group homomorphisms. So I can define it LS category of group homomorphism to be just a map between its classifying spaces. So I remember this B gamma is called Eilenberg-MacLane spaces. Path connected space fundamental group is gamma. Higher homotopy groups are trivial. And this is I think in the exercise in algebraic topology, there is a one-to-one correspondence between group homomorphisms and homotopy of maps between classifying spaces. And since LS category is homotopy invariant, this definition is well defined. Okay, so Jamie Scott in his paper, he stated the following conjecture. So he said that for any group homomorphisms, LS category of group homomorphism is the same thing as a cohomological dimension of group homomorphism. So and he's inspired by this celebrated Eilenberg-Gagne theorem, which said that if given a discrete group, LS category of group equals cohomological dimension of a group. Okay, and here let me give a definition for the groups. Cohomological dimensional group is the supremum of case. The case cohomology of group is not zero for some Z gamma modules. Okay, and interestingly, cohomological dimensional group, it's not defined in the literature, but I found this in the mass overflow, and Mark Grant defines this in the definition. So for cohomological dimensional group homomorphism is a maximum number K such that there exists a Z lambda module with M with non-zero induced homomorphisms. So as we can see that if we take identity homomorphisms, then we recover our classical cohomological dimensional group. And in other words, this is a natural generalization. Okay, now let me go back to this conjecture. What's today's talk, instead of giving a proofs, I would like to give a complete pictures, okay, in this direction. So what's the status? So status is like it's known to if the domain and the target groups are the free groups, it's a part true, and also free abelian groups. And if the homomorphism is injective homomorphism, and it the conjecture is true, it's Jamie Scott proved it. And then, like with my advisor Dranishnikov, we prove also like a torsion-free nilpotent groups. Okay, so and then on the same paper we reduce instead of considering all homomorphisms, just focus on epimorphisms. So if the conjecture is true for epimorphism, it must true all homomorphisms. Okay, and similarly the following year I was able to basically extend it to the finitely generated abelian groups. Then like I was able to extend the torsion-free virtual nilpotent groups, torsion-free almost nilpotent groups. So this type of, okay. And in general, this conjecture is false. So here, like the LS category is 2, cohomological dimension is 1. This is due to the good Willy. But gamma in this case is infinitely generated groups. Okay, and on the same paper, like so with my advisor, we give like a counterexample where the CD of P is 2 and the LS category of group homomorphism is 3. And then the question was when asked, okay, is 2 and 3 are the special cases? Then the following year, like Tranishnikov and his student Adita, they proved that all the 2 and 3 are not special. So it can be like you can have the following CD of phi is k minus 1, cut of phi is k, but k must be at least 3 here. So as you can see from here, so when k is 1 and the gamma is geometrically finite, still open. Okay. So as I said that like for given a homomorphism, so you can restrict it to your codomain to its range and consider only epimorphisms, then we have this result. So basically what it says is that if the conjecture is true for this epimorphism, it must true also for homomorphism by transitivity only. Okay, now since I started cohomological dimensional group homomorphism, and it turns out it's very like interesting by its own. So for example, I was reading a Brown's book. Brown gives the exercise that basically says, okay, prove cohomological dimensional group is a 0 if only if gamma is trivial. Well, natural question arises, okay, well, can I characterize my group homomorphism? So namely the answer is yes. So let phi be like a non-zero epimorphism of finitely generated groups. Then cohomological dimension of phi is 0 if only if phi is a trivial homomorphism. Okay, and the proof is not hard. So then next, until like a famous theorem in the group theory, like it's due to the Starling and Swan. I think they proved cohomological dimensional group is 1 if only if gamma is free group. Well, can we obtain similar result for the like group homomorphism, something that factors through the free group? It turns out like you cannot do that, like with just using a cohomological dimension of a group homomorphism. So you need to bring the LS category as well. So if you bring LS category of group homomorphism and cohomological dimension group homomorphism, then they are 1, then we have a following result. So this group homomorphism factors through the free groups via these epimorphisms. Okay. Then next question is like in the group theory, like Dranishnikov has the product formula for geometrical finite groups. So a natural question arises, okay, can you extend the product formula for group homomorphisms? Yes, like for if you assume the group homomorphism of finite geometrical finite groups, which just means that like classifying space is a finite CW complex. Then we have a product formula. And well, if you look the proof, you can say that, like, I mean, you can prove it for the n, or for it doesn't have to be 2, so it is true for all n. Okay, and also, like, if you look on their papers, it works only if you assume this gamma to be just geometrical finite group. So I'm gonna use these results in my when I presented, like, I think computation on for some subgroup groups for sequential topological complexity. Okay, and part 3. Okay, and now we have on the sequential topological complexity of group homomorphisms. So now let me recall again. So, like, as I said, like, there is a one-to-one correspondence between a group homomorphism and the homotopy maps between classifying spaces. And then because of this fact, we have the following like definition is well defined. So, for example, Ls category of this group homomorphism, I can define it as this Ls category of map between classifying spaces. Similarly, to like sequential topological complexity of group homomorphisms, I can define it to be sequential topological complexity of map between classifying spaces. Okay. Now let me show the computation for finitely generated abelian groups. So in this case, I have to introduce a notion. So we call it the Smith normal number. So we recall that invariant factor decomposition for finite abelian groups. Every finite abelian group G can be written uniquely in the following way, where the integers ni's are called the invariant factors of G and satisfies this following divisibility property, and ni's are cyclic group of all the ni. And the definition is like, given a finite abelian groups, Smith's normal number k of G is a number k from invariant factor decomposition for finite abelian groups. So in other words, Smith's number is, this is a number, this is k. Okay, now let me state that I think the theorem for here, like, let me use like a T of A for the torsion subgroup of abelian groups. And for finitely generated abelian groups, we can define a rank. Well, you take abelian group, you mod it by its torsion subgroups, and then take a rank. Okay, the theorem to like let phi be the epimorphism of finitely generated abelian groups with extra assumption, so where the torsion goes to the 0. Then we have this formula. So in other words, sequential topological complexity of group homomorphism attains its minimum. Okay, and in fact, like, if gamma is a free abelian group, then we have a formula. So the formula says that the sequential topological complexity of phi equals r minus 1 cohomological dimension of group homomorphisms equals r minus 1 times rank of lambda plus like Smith normal number of these torsion groups, torsion torsion abelian groups. And as you can see that, like, this does not depend on the choice of the epimorphisms. So it only depends on this this target group, lambda. Okay, and so then next question becomes, okay, can you remove this extra assumption? And the answer is no. So like, this is it. So like I think due to the Dranishnikov, so for epimorphism from z mod z p squared to the zp, we have cohomological dimension is 2, and Ls category of phi is infinite. Okay, and the proof is like usually follows from this observation. So like in other words, is that a degree zero map from this length spaces that induces epimorphism on the fundamental group. So, and I want to focus on this example more because as we can see that in the classical case, cohomological dimension of a torsion group is infinite. So we are extending this for the group homomorphism case. So we were expecting to get the infinite cohomological dimension of group homomorphism between a finite group to be infinite, but it is false. So in general, so this is a counterexample. So as we can see that for sequential topological complexity, it's bounded below by this LS category of this group homomorphisms, which is infinite. So in other words, sequential topological complexity of group homomorphism is infinite. Okay, similarly, I was able to prove that if I have it a free groups and non-zero epimorphisms, then a sequential topological complexity of group homomorphism is R minus 1 if lambda is an infinite cyclic group, and R if it has more than one generators. So at least two generators. So, and this is true. And as we can see from this example and abelian example, it does not depend on the choice of this group homomorphism. It depends on this target group. So, and it was known that sequential topological complexity of free group, it would be R minus 1 if it has only one generators and two otherwise. Okay. Similarly, I can prove it in other words, I extended for the for no let phi be non-zero epimorphism of surface groups. Then we have this following estimate. So as we can see that I was able to compute explicitly in this abelian case and the free groups, but the rest I just get estimates. So basically what I'm saying is on the free groups, not the free groups, surface groups. So we have this James Scott conjecture holds. In fact, we have this estimate. We can estimate below R minus 1, above by R, and similarly, if the LS category of phi equals CD of phi equals 2, then we can have this estimate. So as you can see, the estimate comes from this product formula that I mentioned in the part 2 part. So here to recall the surface group that I meant at the fundamental groups of orientable closed surfaces where the G's are genus numbers. Okay, remember it's here I'm also considering it torus. Okay, it doesn't have to be just hyperbolic surfaces. Okay, so next, well, since I computed the LS category of group homomorphisms of nilpotent groups, it's a natural thing that to extend it for sequential topological complexity of group homomorphisms. So let me recall nilpotent groups. So we have an upper central series for given a group. It's a chain of a subgroup that we started identity and then we build it recursively. So Z1 is the center of this gamma, and we can define Zi plus 1 is the pre-image of under this canonical epimorphisms of center of this group. And we say gamma is nilpotent if this chain terminates for some n. Then the list such n is called nilpotent class of gamma. So we denoted nil. So from this definition that we can see that abelian group is a nilpotent group with nilpotency class is 1. Okay, so now the theorem said if I have it like epimorphism between finitely generated torsion-free nilpotent groups, then we have this estimate. So here I can estimate it just like using a target. I think using it target groups. So in other words, R times the cohomological dimension of lambda below by R minus 1 cohomological dimension of lambda. And here I put virtual nilpotent groups. Here, I mean, I can also, since I computed like a LS category of group homomorphisms of virtual nilpotent groups, I can obtain similar results. Okay. And namely, I mean, it's exactly the same. It's like, okay. Then also since I computed for LS category for group homomorphism for almost nilpotent group, I can obtain the following results, but remind you that what is almost nilpotent groups, it's a group, it's a semi-direct product of this torsion-free nilpotent group with infinite cyclic group, with P is defined as a one parameter group. So in other words, you can think it as being like you take a infinite cyclic group and you extend it by the nilpotent groups. Okay, then if I have this, then like the following theorem says that like let P be epimorphism between torsion-free almost nilpotent groups such that like if I restrict it on the Z part, I get identity. Then I have the following result. So sequential topological complexity of phi is bounded above by R times cohomological CD of lambda plus 1, below by R minus 1, and times CD of lambda plus 1. Okay, so this once we do computation for LS category of group homomorphism for almost nilpotent group, it just follows from the product formula. Okay, and so yes, so here basically this follows from this result. So if I have an epimorphism between torsion-free almost nilpotent groups, and that where F is restricted to the Z is identity, then we have the following cut of F equals to the CD of F equals CD of lambda plus 1. Okay, and okay, so I would like to basically end this talk by asking these following questions. And the first question is the following equality is true for epimorphisms of geometrical finite groups? So as we see from Tranishnikov example that if we have a finite groups, then this inequality is not true. Or this should be inequality, sorry, yes. I think. And what about for the geometrical finite groups? So namely for the torsion-free groups. Why I'm interested? Because I'm interested on this question too. So the question too is basically I want to know what's the gap of LS category and cohomological dimension of group homomorphism of geometrical finite groups. And if we go back to the part 2, where I give you a complete picture. So as you can see that for the counter example, we only have this. So I think the gap is 1. So when we have a geometrical finite groups, so I was wondering maybe can you can we have a gap 2, gap 3 because here these two counter examples it's actually we use the same manifold here. Like you take a same manifold, you basically product with a torus to obtain this result. But I was more wondered, can we have it like a different counterexamples? Okay. I think that's all I have. I think this is the references. And yeah, thank you for your listening. Yeah.
Thank you very much, Nursultan. If everyone would unmute and give the speaker a hand, that would be great. And are there any questions? Actually, your last question was the one I had throughout. What is the gap between these two things? What if I take your example with category of phi equals k and category or CD of phi equals k minus 1, and if I just take a product of the two spaces?
Yeah, it does. Yeah, I tried that because what we did on this example, we had the both manifold. And
yes.
then this like a product of this two both manifold. So in other words, it's like, yeah, that question you might have a 6 but 4, like that was expected, but I cannot prove it. Like the 4 part, I can prove the 6 part, which just follows. So because they are geometric finite groups, so by Dranishnikov result, it must be 6. And but I cannot prove. I cannot prove that the 2 part, the 4 part. That's
I see.
Yes.
And so for the three-dimensional nil manifold that we usually take,
Yes.
there's a map down to the two torus. It's
Yes.
a principal bundle over the two torus.
Yes. Yes.
And there we would see that just for ordinary TC, we'd get 2 less than or equal to TC of phi less than or equal to 4, right?
So
yes,
I think
4.
if I remember that case, so it's basically it's like by above is by 5 because of the Professor Grant's the result, because you take away the center from like 2G minus the center, which is 5.
Yeah, that's the space itself for the actual map from the nil manifold to the two torus. I think it's between 2 and 4 from your result about nilpotent groups.
Yeah, I think in my case would be just 4. Like LS category is going to, it's 4. Yeah, it's not 5. It must be 4.
All right, good.
Yeah.
Okay, any other questions?
I thought of a suitably brief question, I think. So what to you should be the geometric dimension of a group homomorphism? And do we have examples where the geometric dimension is bigger than the cohomological dimension? Probably, I guess, yes, because the category, we have examples where the category is bigger than the cohomological dimension. But
yeah, I mean, like when we consider for the group homomorphisms, this cat turns out to be our geometrical dimension.
Oh, it's just equal to,
yeah,
right?
Yeah, it's equal to, yeah.
But is it sort of like the minimum K such that the classifying map lifts through the K skeleton, or?
Yes, it can be deformed to the to the K skeleton, yes.
Okay. No, that's always equal to category. Yeah.
Yes.
Mm-hmm. So there are counterexamples to the Eilenberg-Ginea conjecture for maps, but could you ever try and use them to get counterexamples to the ordinary Eilenberg-Ginea conjecture? Seems unlikely now. Now that there are counterexamples in every dimension, it seems less likely. Yeah.
Yes. So yeah, basically what I was trying to do is like a punchline is like I have to do computation for LS category of group homomorphisms. So if I can get a result for that, I can have some estimate for this TC or sequential topological complexity. And but it's like, yeah, computing these guys are hard.
Right. That the reason
go ahead, Mark.
I was going to say that the reason I started thinking about this cohomological dimension of homomorphisms is because in the paper you mentioned, where I got an upper bound for TC of nilpotent groups, it was because you can the map that mods out the center, or rather the diagonal image of the center, gives you a map on classifying spaces, and the category of that map is an upper bound for TC of the group.
Yes.
So then how do you get upper bounds for the category of that map? And I was thinking maybe the cohomological dimension of that homomorphism would be an upper bound, but you've shown now that that's not the case in general. But
yes,
yeah,
I think like, yeah, like, I mean, if I have, if I may, like, I mean, like I put some details, like for example, this nilpotent, almost nilpotent groups, usually like this is a zero map. Okay, so I think, so yes, this is like a two big results. So like, for example, like the first nilpotent, we consider nil manifold. So like basically, if you can realize any epimorphisms as like a basic fiber bundle with like the fiber being connected or nil manifold, then this induced homomorphism is non-zero. This is the result what we are using. So how I extended for the almost nilpotent group, it turns out I found it like a result by this citers in the Lie theory. They have basically, if I have like two simply connected solvable Lie groups, G contains a lattice for any homomorphism from gamma to the H. There's unique extension homomorphism. So I can always extend it. This is the key part. Because as you can see that I started with discrete group. I started with lattices. And obviously I can do completions to get like a simply connected Lie groups. And the question is, can you always extend this like uniquely? So if you can extend it, then we can have like conjecture would be true. And I can extend it only for almost nilpotent group. I cannot do it for the polycyclic group because like here, the key part is completely solvable. So here, like the basically adjoint operator must have real eigenvalues. And so yeah. So, yeah. I don't know if it's helpful or not. Yeah.
mm-hmm.
Okay, anything else? Well, if not, then let's thank our speaker again.
Okay. Well, thank you.